So, use of Maclauren series, particularly for the exam purposes for the Year 2 exam, will be to use Maclauren series to help us to integrate a function like this. This is not a straightforward function to integrate, because if we're integrating with respect to x appears twice. So it's not straightforward to integrate. The easiest way to do it is to recognize that log, the natural log of a function like 1 plus x, can be expanded as a power series using Maclauren's theorem. And then we can multiply that power series, each term in this power series, by x squared, and we'll end up with a series of terms that we can then easily integrate, because we integrate each one independently, separately, and then we can put our limits in of 0 and 2. So let's go through this process and see how it works. So we take the natural logarithmic part of the function. So we look at the function, or the part of the function, which is the natural log. And we're going to expand this using Maclauren series. Theorem, which is a way of writing each of the terms in the power series. So the first step is to set up a little table like this, where we have the function we're going to expand, which is the log of 1 plus x, on the left hand side here, and then we're going to try and calculate what the first differential of this is, the second differential is, the third differential is, and fourth differential is, and so on. So we just keep differentiating over and over again this function here. And then when we've done that, we find out what is the value of the function when x equals 0, and put that in here. What's the value of the first differential when x equals 0, second differential, third differential, and so on. So this table is set up to do that. The first differential is probably the most awkward, actually. The log of 1 plus x, if we differentiate that, becomes 1 over 1 plus x, multiplied by, using the chain rule, we let u equal the 1 plus x. So it's 1 over 1 plus x multiplied by the differential of 1 plus x, which is just 1. So it actually turns out to be 1 over 1 plus x. So if that wasn't a 1 in there, we'd have to multiply by the, if it was, say, 1 plus 2x, then it would be, the differential would be multiplied by 2, because the differential of 1 plus x, 2x is 2. But in this case, it's just 1 over 1 plus x. It's 1 over whatever is in here, whatever is inside this bracket, multiplied by the differential of that. And in this case, that's just 1. So that's the answer, which is, using the laws of indices, and that's the way we really need to write it, 1 plus x to the minus 1. Again, using the chain rule to differentiate this, we differentiate the whole bracket, so that'll be minus 1 bracket 1 plus x to the minus 2, because we take 1 off the power, and then we multiply that by the differential of what's inside the bracket, and in this case it's 1. And in all the cases we're going to see on here, that always ends up being 1, but not necessarily if you've not got a straightforward function inside the bracket. If it was, say, 1 plus x squared or something, we'd have to worry about that. So the next differential, bring down the power, minus 2 times minus 1 is 2. 1 plus x to the power minus 3. Write down what you think the next one will be. Yep, hopefully you get minus 6, 1 plus x to the minus 4, and so on. We can carry on going. Next term, the fifth differential, what would that be? So the next term will be 24, 1 plus x to the minus 5, and so on, for as many terms as we want to do. And as Dan pointed out earlier, the more terms you have, the more your power series gives an exact answer for the function. Now, what we're really interested in is what the values of these differentials are when x equals 0, because these are the numbers that go into Maclauren series. So we just take each of these, 1 plus x to the minus 1, minus 1 times 1 plus x to the minus 2, and so on, and let x equal 0 and work out what the answer is. So the first one, if x is 0, we want the log of 1. What's the log of 1? The next one, if you look at this bracket, and in fact all the others, if x is 0, these are all 1. So in fact we can forget about the powers, because anything to the 1 to the power anything is always going to be 1, isn't it? So these are all 1. All we got to think about then is what's the number in front? Minus 1, 2, and minus 6. So in fact it turns out that the first differential when x is 0 is just going to be the number in front, which in the first case is just 1. And so we can see the coefficients are just 0, 1, minus 1, 2, minus 6, 24, and so on, for as many terms as we want. So what do we do next? What do we do with these values? So next step, write down Maclauren series. And what we've just done is found out these numbers here that go in front of the x. So what's that saying? It's saying that our function, which in this example is the log of 1 plus x, can be written as the value of the function at 0, which was 0, plus the first differential, which was, to look back, 1 times x. The next was minus 1, so that's minus 1 times x squared over 2 factorial, and so on. The rest of the terms, 2x cubed over 3 factorial minus 6x to the 4 over 4 factorial plus 24x to the 5 over 5 factorial. And actually a pattern's starting to emerge, but we can't see that unless we work out what these are. What is 24 over 5 factorial? What is 6 over 4 factorial, and so on? So if you just work out what they are, in other words, simplify these, you'll see the pattern. So simplifying, we can see a pattern. 0 is the first term, 1 times x is just x. Next term is x squared over 2, because 2 factorial is just 2. And we see we actually end up with x cubed over 3 minus x to the 4 over 4 plus x to the 5 over 5. So we can actually anticipate the next term, minus x to the 6 over 6, and so on. Okay? So that's our power series that represents log 1 plus x. So this, effectively, is the power series for log 1 plus x. So looking back to our original problem here, we had to integrate this. So now we can replace log 1 plus x with its power series. Okay? So we've got the integral of x squared log 1 plus x can be written as the integral between 0 and 2 of x squared times that power series that we had written down. X minus x squared over 2 plus x cubed, x to the, what was it? Yeah, over 3 minus x to the 4 over 4 that would probably do for the number of terms. And in an exam situation, you'll be given a clue as to how many terms to go to. So what do I do now? Yep, expand out those brackets. X squared times x, x squared times minus x squared over 2, and so on. So expand out the brackets. And we end up with this, which is just a series of terms that we can integrate using the basic law of integration. Add 1 to the power and divide by the new power. So now see if you can carry on and finish this problem. Integrate and then put in the limits 2 and 0 and see what you end up with as the value for the function or the area under the curve. So that gives this as our integral, adding 1 to the power and dividing by the new power in each case. Now all you've got to do is put the limits in. Notice if one of the limits is 0, by the way, do have a look at it, because if x appears in all the terms, then the second limit is going to be 0, so you only need to worry about the first limit. So answer 6.18. So just quickly to recap on this question, if you have a question like this to do, where you've got to integrate a function like this, where x is appearing twice, that's not a straightforward integral. So one technique you might use, especially if you've got something like this in there, is to expand it out. So if you've got some sort of trigonometric function like sine or cos, or you've got the exponential function, or you've got this natural log function, you might use Maclauren series to expand it out. And to do that, you set yourself up a table where you can find out what the value of the function is when x is 0, what the first differential is, second differential is, third differential is, and so on. So you end up with these values here, which go into Maclauren series, and replace these here. And then you tidy up. Often when you tidy up, you end up with a nice pattern emerging. So you put these numbers into the Maclauren series, and then tidy up to get the power series, and then you replace log of 1 plus x in this particular case with the power series, expand out the brackets, and then you can easily integrate what's left, because it's just a case of integrating each term in turn.